Good afternoon. I expect that you have had a little rest from this morning session and a little food to get energy to keep on going in this in this afternoon. We have now a session dedicated to fusion and fission. And the first speaker is Professor Ricardo Betti. He's chief scientist in the Laboratory for Laser Energetics, and is also professor of mechanical engineering and physics and astronomy in the University of Rochester, New York, which is a cooler place than Madrid, I guess. Okay, Professor Betti, you have the word.
Thank you. So thank you. I would like to thank the European Academy of Science for inviting me to give this talk. And so I'm giving two talks, one today and one tomorrow. And today's talk is about an achievement that took place at Lawrence Livermore National Laboratory. I'm at the University of Rochester, but I'm a close collaborator with the Livermore Group, so I hope I'm going to do justice in describing the achievement that they achieved. Probably you heard in the news the achievement of ignition, thermonuclear ignition in the laboratory for the first time. So, so the National Ignition Facility, this is the largest laser in the world. Lawrence Livermore National Lab is really the flagship fusion facility in the United States. It's a very large laser hosted in this building right here, and is the size of 3 football fields. It's 192 laser beams. There's a called frequency tripole. It means the light is in the UV, has an energy of 2.2 megajoules of laser output, 2.15 to be exact, but probably getting to 2.2 in a few weeks. A maximum power of 480 terawatts and a wavelength of roughly a third of a micron. Construction of the NIF started in 1997, and it was completed in 2009 when it was commissioned, and has been operating since 2009. So the nuclear fusion reaction that is used on the NIF and in most fusion facilities in the world is the fusion of deuterium and tritium, which is the most common fusion fuel in laboratory experiments. So deuterium and tritium is the reaction that gives helium, which is an alpha particle, that gets roughly 20% of the total energy, 3.5 MeV, and then a neutron with roughly 14 MeV. And just to give you an idea of the energy that one can extract from deuterium and tritium, if you can fuse a kilogram of DT, you will get 340 terajoules of energy. And if you compare to the first atomic bomb, that produces about 60 terajoules. So that gives you an idea of the magnitude of the energy that you can extract from fusion. And deuterium and tritium is the easiest fusion reaction to initiate. And also has some nice features like the production of a charged particle, which is helium, the alpha particle, and then I'll show you why that's important. So here you can see a plot of the so-called fusion reactivities. So you can think almost of like the probability of triggering a reaction. It requires high temperature in the reactants. The temperature here is given in kiloelectron volts. So just remember that roughly 1 keV is equivalent to 10 million degrees Celsius. So as you can see, this is in logarithmic scale. So the probability is very low when the temperature is low, and increases rapidly with temperature. So if you want a decent probability of fusion, you really need to operate a high temperature, and this is 10 kiloelectron volts, so 100 million degrees. So those are the temperature that you really need to operate at if you want DT fusion. And if you look at the probability, this probability of reaction is a lot higher for DT than other form of fusion of light nuclei like the helium-3, deuterium-deuterium, proton boron, or helium-3, helium-3. And the reason why you need these extremely high temperatures is that because at these temperatures, the electrons are stripped from the ions, so it's fully ionized, and therefore you need to overcome the Coulomb repulsion in order to fuse. And therefore, if you had to smash one nuclei against the other at very high velocity, that's why you need a very large temperature in order to fuse. So as I mentioned before, one important ingredient of this reaction of D and T is first that you have neutrons, and the neutrons just leave the plasma. They carry most of the energy, like 80% of the energy. And then 20% of the energy is in the alpha particles, in the helium. The helium is charged, the alpha particles are charged nuclei, so they collide with the electrons, and they transfer energy to the electrons. Then the electrons gain this energy, and then these electrons collide with the ions of deuterium and tritium and transfer the energy back to the plasma. So you can think of this as a positive feedback mechanism for which the fusion reactions produces alpha particles. The alpha particle deliver energy to the plasma itself, first the electrons, and then from the electrons back to the ions. They increase the temperature, and if the temperature goes up, then the number of fusion reactions goes up, and so this can become an unstable feedback, which can cause what is called a thermal runaway or thermonuclear instability that is called ignition. So ignition is really the point where this positive feedback is triggered. And so getting to this, triggering this positive feedback has been a kind of a 60-year-long quest and effort in the fusion community to trigger it. Okay, so it's very difficult to trigger it. And I'll show you what are the conditions for triggering. So when I talk about laser fusion or inertial fusion, is a special kind of fusion, different from magnetic fusion. In this case, the triggering of ignition is caused by compressing a pellet that contains the fusion fuel, deuterium and tritium. This pellet is compressed by direct illumination with lasers, or you use lasers to make X-rays, and then you use X-rays to implode the capsule. So basically, you ablate the surface of the capsule. Conservation of momentum, the capsule implodes inward, and as it implodes inwards like a rocket, then eventually it stagnates in the center, and when it stagnates in the center, if it reaches the condition for ignition, when obviously it's accelerated at high velocity, and then eventually as it converges, it will stagnate, and so all the kinetic energy is transformed into internal energy, which is pressure. And if it reaches the condition for ignition, then ignition, like ignition of gasoline fuel, then ignition will propagate through the entire fuel that is compressed and will generate a lot of fusion energy. So what was done at the National Ignition Facility, the big laser at Lawrence Livermore, was accomplished through the so-called indirect drive approach. Where 192 laser beams, half from the top and the other half from the bottom, shine inside a cavity which is made of high Z material, typically gold, and can be coated with depleted uranium. And when the laser light hits the inner walls of this cavity, which is called the hole round, hits this cavity, the inner walls, to hundreds of electron volts, and emits X-rays at the temperature of roughly 300 electron volts. These X-rays ablates the surface of the capsule. It generates an effective pressure on the surface of roughly 100 million atmospheres, so 100 megabars. And this implodes, therefore, at high velocity, reaches roughly 400 kilometers a second of inward velocity. And then when this capsule stagnates in the center, it generates a pressure in the center or a few 100 billion atmospheres. And those are the conditions are right, then you will have ignition of the DT fuel. And that's what happened at Lawrence Livermore in December 5th, 2022, producing 3.15 megajoules of fusion energy for 2 megajoules, 2.05 megajoules of laser energy entering the hole round, of which 2 megajoules were absorbed by the hole round itself, 250 kilojoules of the X-rays were absorbed by the surface of the capsule, and about only 30 kilojoules of that became kinetic energy of the implosion. So I'm going to go over this energetics in a little bit. But now one has to remember that in order to produce 2 megajoules of laser energy, one needed 300 megajoules of energy stored in the capacitors that drive the laser. So first, one has to keep in mind that driving ICF targets with lasers is a very inefficient process. As I said, the energy has to go first into heating up the walls of the hole round and making X-rays. Then the X-ray energy goes into ablating the plasma from the surface of the capsule, which is made, in this case, was made of carbon, high-density carbon. So most of the energy goes into heating up the carbon. And at the end of the day, what really matters is the energy that is acquired as form of kinetic energy of the implosion. And that kinetic energy, it's only 30 kilojoules out of 2 megajoules of laser light shining inside the hole round. So in terms of efficiency of this technique, the efficiency is 1.5%. 30 kilojoules is the energy that really matters to trigger ignition. And you need 2 megajoules of laser light to get the 30 kilojoules of kinetic energy. All right? And so it's a very inefficient process. So when the capsule implodes and gains a kinetic energy and a velocity of 400 kilometers a second, it has nowhere to go that converge inward, and then eventually will have to stagnate. And when it stagnates, it makes a central plasma that is very hot, roughly at 50 to 60 million degrees Celsius, so 5 to 6 keV. And then it's surrounded by a dense, almost what you call it, a dense shell. It's a dense DT. There is a lower density DT in the center that is hot, and then there is a high density in the hundreds of grams per cubic centimeter DT that is colder and surrounds it. And this dense cold DT provides the inertial confinement of the central plasma. So at the end of, let's say, a stagnation, you will find the plasma where the temperature looks something like this. This is temperature versus radius stagnation. It's in the center, reaches 6 kiloelectron volts, and then is relatively cold, where the density goes from relatively low density, few tenths of gram per cc, up to hundreds or 1,000 grams per cc around it. And it's this dense plasma that confines the pressure of the central plasma, which is the one that ignites. So when you look at fusion plasma, this is general, whether it is inertially confined or magnetically confined, you always look at the figure of merit, which is the energy that you use to heat up the plasma and the energy that the plasma produces on its own to heat itself. And the energy that the plasma produces on its own is the energy of the alpha particles from the fusion reactions. And I remind you that the alpha particles gain 20% of the energy, the total fusion energy produced. So that goes back into the plasma. So the plasma gets two forms of energy. The external input energy, that in the case of inertial confinement is compression work. We call it PDV work, just compression work, like a piston. The shell is compressing the central plasma like a piston. And then there is the energy from the fusion reactions themselves through the alphas. And the ratio is called Q sub alpha, is a measure of how important is the fusion self-heating with respect to the external heating that we are supplying through the laser and all the different stages of the implosion. Now, we call a burning plasma a plasma where the alphas are the largest energy source to the plasma. So E alpha over the external energy supplied is larger than unity. And then an ignited plasma, then that's it's an instability, it's a thermal runaway. So then the fusion heating is much, much bigger than the external energy supply to the plasma. So the progress in fusion research is really determined by this factor, Q sub alpha. The first milestone would be Q sub alpha above 1. That means that the plasma is dominated, the heating of the plasma is dominated by the fusion reactions themselves, so self-heats, and then an ignited plasma where you trigger the instability. So the condition for ignition is that the so-called Lawson criterion that Professor Volpe mentioned this morning can be expressed as the product of the pressure and the confinement time. So you have to reach a given pressure and confine it for a given time for ignition to take place. And this product has to be larger than 10 atmospheres per second. That you can also rewrite it as 10 gigabars per nanosecond, depending on your time scales. So magnetic confinement operates on it, for instance, say a big tokamak like the ITER tokamak, on a time scale of seconds. So the plasma has to be up tenths of atmospheres in order to ignite. Inertial confinement operates on the time scales of a fraction of a nanosecond, and therefore requires over 10 gigabars to ignite. The NIF laser-driven implosions, they would have a confinement time of roughly a tenth of a nanosecond, 100 picoseconds. Therefore, they would require pressures over 100 gigabars in order to ignite. So the ratio of P times tau divided by this constant is called the normalized Lawson criterion. And when this is unity, you have ignition. When this is below unity, you don't. So the whole goal of a large portion of the fusion research effort in the last 60 years is to achieve the condition where this parameter chi is above unity in the laboratory for the first time. This has been accomplished in thermonuclear devices before, but never in the laboratory. So as I said, the progress towards ignition is assessed by increasing values of the Lawson parameter. So this is the Lawson parameter chi right here, P tau divided by the 10 gigabar per nanosecond. And this is the amount of self-heating from fusion. So as we have been increasing the value of chi, let's say up to roughly 0.8. At 0.8, we would have a plasma that is dominated by fusion reactions, but it's not ignited. In order to get to ignition, then we need to reach chi equal 1, and then you would have the self-heating from fusion skyrocketing and dominating a great deal over the external heating. So this is the burning plasma condition, chi larger than 0.8, Q sub alpha larger than 1, and this is the ignited plasma condition, chi 1 and Q alpha much greater than 1. So this is the kind of a brief history of the laser fusion effort in the United States. Just right after the first thermonuclear device in 1952 was tested in the Pacific, then scientists started thinking about inertial confinement fusion. And then with the invention of the laser, of course, the scientists thought, well, let's use a laser. And the first paper then on Nature in 1972 by John Knuckles et al. Proposed the use of lasers for reaching ignition in the laboratory. So then lasers have been built at Lawrence Livermore. So this was lasers rather small compared to today's standards. You can see the energy, 1 kilojoules and 1 omega. So those are in the infrared. And then those are a 20-beam system, a Shiva. There was also there was a 10 kilojoule laser in the infrared. And then Omega, this is at the University of Rochester, that's my institution, was a 3 omega laser. So this was a laser with frequency tripling, so it was in the UV. Then Nova, 30 kilojoules, also in the UV. then omega, this is a Livermore, then omega 60 at Rochester, 30 kilojoules in the UV, 60 beams. And then the Z facility, this is, was a pulse power facility, also to study fusion, but using pulse power rather than lasers. And then the National Ignition Facility at Lawrence Livermore broke ground in 1997, start operation in 2010, 1.8 megajoules of laser light at 3 omega, so in the UV. And then the first ignition experiment took place in 2011. And then I'm going to discuss what happened in the last 3 years, from 2020 up to the demonstration of ignition. So this is what happened in the last 3 years. And this was really rapidly, the NIF achieved the first, the burning plasma conditions. So back in 2020, a Nature paper was published by the Livermore Group and collaborators, where they achieved for the first time a plasma that was dominated by alphas. So Q sub alpha was between 1 and 2. So the alphas were the dominant heating mechanism of the plasma. And the normalized Lawson criterion was 80% of the value required for ignition. But then about a year and a half later, then they achieved ignition for the first time. The Lawson parameter was unity, and Q alpha was roughly 2030. The fusion yield was 1.35 megajoules for 1.9 megajoules, 2.05 megajoules of laser light into the whole round. And then more recently, December 5th, 2022, they achieved the target gain above 1. So target gain above 1 means that the fusion energy output, which was 3.15 megajoules of fusion energy, exceeded the laser energy shining on the target. So the laser energy was 2 megajoules, and the output was 3.15 megajoules. So there was a gain, target gain of 1.5. So for the first time, in this case, we have an experiment where the laser going into the target, not just into the plasma. Remember, into the DT, what goes into the DT is minuscule amount, only 30 kilojoules. But all the other energy is basically wasted in making X-rays, and the X-rays heating up the ablator of the target, which is made of high-density carbon. But what goes into the DT is only 30 kilojoules. So just a short description of the challenges to get there. So this is a major challenges in the path to ignition. One major challenge was to make the targets with the right specs, and that means to make it as uniform as possible. The rationale for making uniform target is that because if you have imperfection on the target, this is how the target looks like. So the target has an outer shell which is made of high-density carbon. This is the latest version of the Livermore targets. I have high-density carbon as the ablator. So the X-rays shine on the high-density carbon. And then inside there is a layer of DT ice. Typically the thickness, this is the size of this target is roughly 2 millimeters in diameter. The outer shell is roughly 80 micron thick, and then the DT ice, which is frozen DT at the triple point, which is 18 Kelvin, is roughly 65 micron thick. So, so if you have imperfection in the target, like little voids, for instance, or little pits in the target, then because the implosion itself is hydrodynamically unstable, instability will cause material from the ablator, which is carbon, to mix with the DT. And once you have mid-Z material mixing with low-Z material like DT, the amount of radiation that is emitted is a lot higher. So there is a lot of radiation losses. And radiation losses, of course, require that then you need more energy to bring the temperature to the ignition level. So that phenomenon of mixing the ablator material with a hot DT is called mix. And the problem of mix is it's a very important problem that has to be solved. So one of the things that had to be done is to make this target as smooth as possible with fewer defects. If you can see here, this is the target that was used. This is the whole round. This is about a centimeter it's a cylinder, it's a centimeter in length. Inside the whole round, there is this little capsule here, which I said is about 2 millimeters in diameter. And the initial design for the Livermore capsule had a beryllium ablator. That evolved into a plastic ablator, CH, and that evolved again into a pure carbon ablator called high-density carbon, HDC. And this is the target that actually ignited. Those targets did not. There is a lot of refined science into designing the laser pulse shapes. This is the power of the laser versus time. So they see all these features of the pulse shapes that had to be designed perfectly in order to have a perfect implosion. Remember, the implosion has to converge a factor of roughly 30-35 in order to work. This is the actual target that ignited. This is the size of the whole round. You can see it's about a centimeter in length. 3.64 millimeters 3.64 millimeters was the hole where the laser entrance hole for the laser beams. And this is the laser pulse shapes used to trigger ignition. You can see there is a lot of sophistication in the designing all of this. So it took a while to get everything right. As another major advancement, to get the target just perfect. This is X-ray contrast imaging of the target itself. You can see imperfections here. This is a target that did not ignite. It gave 100 kilojoules of fusion energy. For the same pulse shapes, a cleaner target without these defects gave 1 megajoules of fusion energy. So to get the target perfect is essential. Increasing the laser energy was also a major factor, even if the increase was only from 1.9 megajoules to 2.05 megajoules. You can see here the laser pulse shape, energy, power over time versus time. You can see that by increasing the energy, one was able to extend the laser pulse a little longer and keep pushing the target a little more. Yes, done. So this is my conclusions. So questions on whether a powerful laser can ignite thermonuclear fuel in the laboratory have been put to rest. So we can ignite DT in the laboratory. This is the first time it was ever done. It was a major effort with contribution from many institutions listed here. What comes next is robust and repeatable ignition. We should be able to do this many times. Every time we design it, it should work. To get high energy gains out of this, not just a gain of 1.5, but gains of 10, 20, and eventually for laser fusion energy application, gains of 100. And then now exploring the feasibility of turning this into an energy source will be laser fusion energy. Thank you.
Thank you, Professor Betty. There is at least a question. It works?
Yes, my question is, how do you get a uniform compression of the target when the laser light is coming in from two ends?
Yeah, doesn't make sense, doesn't it?
No.
Yes, so no, you're right. That's one of the problems, right? Because you are compressing a sphere with a cylinder, and there is a mismatch of geometry, right, over there. So the way it's done, so let's see if I have it. No, back here, back. See if I have a picture of this. I think, a second, I had it. Can we see that here? Let's see, 1 second. Okay, so you don't see, you see that there. So as you can see here, this is the laser power versus time. The laser is split into two different cones. So there are a cone that's called the outer beams, and a cone that is the inner beam. So the inner beam are pointed towards the equator of the hole realm, of the cylinder. And the outer beam are pointed towards the edge of the cylinder. So that still is not a perfect illumination. So you're not illuminating the wall of the hole realm in one point. You are distributing the beams to illuminate the whole realm as uniformly as possible, but you had to send the beams to the equator, which is around the equator of the capsule, because that's the one that is lacking the drive. And so you had to design it in such a way to make it in a time dependent, to make this push to be as uniform as possible. It's never perfect. So you have a no uniformity in the implosion. It's called the P2, which is the Legendre mode 2, because you squeeze it to be either a pancake or a sausage, so an elliptical squeeze. So you had to drive it in such a way that you compensate the drive at the equator and the drive at the pole. That's a difficulty, but you learn by trial and error. So.
Thank you. Well, a second and last question.
Oh, okay. Well, thanks, Ricardo. That was really fantastic and a big achievement. And really, very general question. What is the impact in, I mean, of course, you want to have more energy than what you put in. What is the impact of the cost or the energy involved in making the DT fuel? Is that really important in the general energy equation?
In the energy equation for what applications?
Yes.
Okay, so
exactly.
if you're thinking about energy applications, then of course everything matters. So all this research is funded not for energy. This research is funded for.
But that's my question. I mean, if from regular hydrogen, how much you have to spend in energy to make the DT fuel, and then
because you had to cool it. That's what you're saying.
Well, you have
to make well, that goes into the total energy budget. So that's why it's not a done deal that you can turn this into an energy source. So there are many steps before that is possible. As what you mentioned is one of them, but there are many others.
Yeah.
Okay, so you have to make the lasers a lot more efficient. This is the case where you have 300 megajoules going into the capacitor bank, and then you produce 3 megajoules of laser energy, of fusion energy. So you have to do all the accounting. For
maybe
all
we'll learn more about this in future talks.
Okay, let's thank the speaker again. Thank you, Professor Petty. Well, yes, Professor Donnet is the program manager and CRO in Eurofusion, and we have to thank him very much in advance because he was in Granada this morning in a seminar, and then he's come here. He has to leave because he has another meeting tomorrow in Germany. So really, he has made a big effort to be among us today. So thank you for coming.
Thank you very much, ladies and gentlemen. It's a real pleasure to be here. It has been a rush. I just had the longest taxi drive in my life from Granada to here to be in time. And immediately after my talk, I need to rush to the airport to catch my flight. So Mike, thanks for your flexibility, although you didn't have a choice here. But I understood after hearing Ricardo's talk, there's a little bit of overlap. I think also I have kept the level a little bit simple because I didn't know what the public was today, but I don't think that's too big a problem. I have one slide on what we are, Eurofusion. We are a consortium of 31 national research institutes in 29 countries. Only Germany has 3 national research institutes. In Spain it's CIEMAT, here in Madrid. And behind these universities there's 164 universities. And in total there's roughly 5,000 people involved, researchers but also PhD students. Now, every day when we read the newspaper, you see news about the climate change, global warming. At the same time, we see news about the energy crisis, especially after Ukraine was invaded. So we need to do something. And in principle, many forms of energy we use, they have their origin in the sun. It's clear for solar energy, of course. Wind energy is driven by temperature differences on Earth. But also fossil fuel energy is indirectly, plants which have grown here millions of years have been covered by sediments and now turned into coal, oil and gas. So the question is, why can't we use the energy source of the sun directly here on Earth? The sun works on nuclear fusion. Nuclear fusion is clean, no CO2 emission. It's safe because we can't have, let's say, a meltdown, a chain reaction. No long-lived radioactive wastes. It's baseload electricity. You turn it on and you have the energy. You don't have to wait until the wind blows and until the sun shines. Although yesterday in Granada there was a lot of wind and even trees fell down. It was amazing. It has a small geographical footprint, so you don't need large surfaces covered with solar cells and wind plants. And the energy is abundant. The constituents, deuterium and tritium, or actually lithium, from which we breed the tritium, are well available. So I think I will go quickly through this. We make use of the deuterium-tritium reaction that was already explained. Deuterium occurs abundantly in nature, and in every liter of water there's 33 milligrams of deuterium you can easily get out. Tritium we don't have in nature because it has a very short half-lifetime of 12.5 years, but we can produce it from lithium. I will show later how we do that. And this is the fusion reaction which was already explained, so I will not do it again. What is important to remember is that we stripped here the atoms from their electrons, so the deuterium and tritium atoms are positively charged, and you need to have a lot of energy to make them fuse. Also, the helium is positively charged, and we make use of that because when we create a helium particle, we want to it to turn its energy again to heat the hot plasma. And a neutron doesn't have a charge, and we make use of that. This picture was already shown, and it shows why we use deuterium-tritium. There's some groups in the world which are focusing on proton-boron or deuterium-3 helium. The difficulty with these reactions is you need to go to much higher temperatures. Proton-boron, for instance, the optimum temperature is 125 kilovolt, and also the reaction rate is lower. The advantage of proton-boron is that you don't have neutrons in the fusion reaction, so it's again somewhat more beneficial for the wall and the materials, but it's much more difficult to get the reaction going. Fusion in the sun takes place at 15 million degrees, but on Earth we need a factor of 10 higher to create the fusion conditions, and this is because in the sun the gravitation, of course, puts the particles already very close together. Now, how do we do that? One way is inertial confinement fusion, and I will very quickly go over here because Ricardo already showed this. And this morning in my hotel I updated my slides to have the 3.88 megajoule on here. I can give you an updated slide to distribute to the participant later. But it's a very nice result, and NIF is the first facility that really achieved the burning plasma state and ignition. The other concept which I focus the rest of my talk about is magnetic fusion. This is JET, the Joint European Torus, which is the largest fusion device in the world, which is operational. It's filled with a very low density plasma gas, so typically the pressure is in the order of 10⁻⁵ atmosphere. We fill it with hydrogen gas, and then we make it hot. You see in the insert on the right side a plasma, and actually there's no light coming from the center of the plasma because it's so hot that all the particles there are fully ionized. So there's no line radiation. You only see line radiation from the very edge. I I think there was this laser here. So from the very edge here, and this is where neutral gas enter the plasma and where particles ionize. And at the very bottom, that's where the diverter, where we lead away the heat from the plasma. I come back to that later. The confinement time is relatively long here. It's in the order of seconds. Now, how do we do that? I made a small animation. I took a glass, or well, at least a transparent vacuum chamber, fill it with deuterium and tritium ions, and then we start heating it. And if you heat it high enough, then the atoms get so much energy that they fall apart in electrons and positive nuclei. And if you put on the heating high, the particles get more and more energy. They have a Brownian motion. They basically can collide with each other and they can fuse. But you see another negative effect. It will also hit the walls here. And that's not good, because then they cool the wall, or they heat the wall and they cool themselves, sorry. So we use here the magnetic field to line up the particles, and the particles now spiral around the magnetic field lines, and it's very much like the runners on a curtain rail, and they cannot go to the walls, at least not to the side walls. You see, of course, still the problem that you have end losses, and to prevent that, we bend the tube in itself. And we have two main concepts here. One is the tokamak, and that's the most important device at the moment, and the one which is furthest in development, and there's the stellarator on this side. A tokamak has the magnetic field with these blue coils here, and then additionally we run a current in the plasma which we induce with a central solenoid. It's very much like a transformer, and the current also induces a magnetic field, and if you superpose them you get this helical magnetic field line. I don't know whether it's visible for you, it's the black lines, and these confine the plasma. So the plasma is actually levitating in this chamber. In the stellarator we use external field coils to make the field. The advantage of the stellarator is that it's a continuous device, and it also doesn't have some of the instabilities a tokamak has, but it's technically a much more complex device, and therefore most people are working on the tokamak. So here you can see a simplified picture of this tokamak. And what we usually do, actually since the early 80s, we make the plasma elongated, which is we can reach better confinement in an elongated plasma, and we make a kind of crossing point in the magnetic field lines. And this means that heat which is coming from the center of the plasma, particles which cross this magenta line, they come in this blue region and they are guided then to the diverter. Here you can see how it works. This is a cross-section to ITER. ITER is presently being built. It will be the biggest fusion device in the future. All the particles in the center, at some point they lose their energy. Alpha particles which have given their energy to the rest of the plasma, we want to have them out. They cross this black line and they come in this brown line, and then they are guided to the diverter. And this is a 2 centimeters thick layer, and if you make all your calculations, you do your best to radiate a lot of power on the outside of the plasma. The heat load on the diverter is 10 to 20 megawatt per square meter. 10 to 20 megawatt per square meter is the heat load you have on the surface of the sun. So we need materials which we can lay on the surface of the sun and which stay there for years without melting. You will say that's impossible. No, we have these materials. And I show you. This is tungsten, ITER grade tungsten. So tungsten we use in ITER. They are actively cooled by water. Of course, in the sun you cannot cool, we can do that. And here we expose them to a plasma of 20 megawatt per square meter. We did that for 18.5 hours because that's about 1 year of ITER operation. And then after operation the tungsten looks like this. Pristine, no damage. You only see in one of the blocks as a black spot. That's where we use the helium plasma, and then we get some blackening, but no damage. The world record on our side is 59 megajoule. So we didn't reach ignition, we didn't reach the burning plasma state. But we have an extended phase where we have 59 megajoule out of fusion. We use only 170 micrograms of deuterium and tritium. 5 seconds is the limit of what we can do in jet, because jet has copper coils, and when we operate the machine at the highest performance, this is really the limit. But it's still quite sizable. Just to compare, it's about the energy you need to bring 100 liters of water to boil. If you would like to do that with coal, you would need 4 kilogram, and with fusion only 170 microgram. And also the energy density, Ricardo already mentioned that, but it's equivalent to a lot of oil, a lot of coal, a lot of gas, and it's even 100 times more efficient than fission. So yeah, it's really important to work on this. This is a kind of comparison in numbers. I often get this question: what is better, what is closer to, let's say, realization? I would say we need both lines in parallel. You can see also in the numbers that let's say we have with magnetic fusion more fusion power reached, but if you look in the Q, it's, well, the new number is 1.9 versus 0.33. So there, let's say magnetic fusion is better. Of course, the extrapolation of our longer pulses is maybe somewhat easier, but we have laser developments on the other side, so I don't want to go in that discussion, apart from saying it's important that we exploit both lines in parallel. So this is how the magnetic confinement plant looks like. We have a big tokamak, a plasma in the center, then we have a wall. We fill the wall with lithium, and the lithium is split in helium and tritium, and the wall will also become warm, and we use the heat then to drive turbines and to generate electricity. So here you can see the full reaction. This is the reaction which I have showed before, and also Ricardo has shown that the neutron doesn't feel the magnetic field. It goes into the wall, where we take care that we have lithium-6. Lithium-7 also works, but as long not as effective as lithium-6. But the lithium-6 is then split in helium and tritium. Also, this reaction gives some additional heat. The tritium we feed back into the reaction, and for a reactor to work, we need to breed about tritium at a ratio of 1.1. So for each tritium which is burned here, we want to create 1.1. We can do that by adding neutron multipliers, so you get a little bit more of these reactions. So with many facilities all over the world, including JAT, we have shown that fusion is plausible. We are working on ITER. I will show a few slides on ITER, which will come, well, this first date is going to be shifted, but the DT operation they still want to have in the mid-30s, in the second half of the 30s. This will show that fusion is feasible, and within EurASc we are working on the design of demo, where our aim is to get it roughly in operation around 2045. That's start of commissioning, and ultimately the power plant. So this is our roadmap. The goal is the fusion power plant. ITER is very important, but will not get there completely, so we need demo to give the electricity production, and that will be around the middle of the century. We do a lot of research in many facilities all over Europe, all over the world. We need to work on materials. I was very happy this morning to open the International Conference on Fusion Reactor Materials, because that's really the item which makes fusion so long. And in Spain we're building now IFMIF donors, which is a 14 MeV neutron source, to test the materials. Stellarator, we're doing research, and this is our long-term backup, and well, of course we're doing also a lot of research to make fusion affordable. ITER, 2 slides. It's a collaboration of, I would say, almost all countries in the northern hemisphere. So Europe, China, India, Japan, Korea, RF, and US. ITER will deliver 500 megawatt fusion power versus 50 megawatt in, so it will have a Q of 10 roughly, and it's now 80% completed. And here you can see a picture of pieces of the vacuum vessel, and there's around them the toroidal field coils. which are now being built. ITER will not generate electricity. It's still fully a research reactor. And then in our offices in Germany, we are designing for demo. Demo should deliver 500 megawatt electric power. That means that the fusion power is in the order of 1.5 to 2 gigawatt fusion power. And we don't want to go over the 500 megawatt electric because then it becomes very difficult to dump the power on the grid. And we're working on the stellarator. Here you see a picture. This is Wendelstein 7X. All these blue and the brown coils, they're superconducting. And we could only make these designs thanks to the supercomputers in the early 2000s. But Wendelstein is already operating. They had this year 8-minute plasma discharge with 1.3 gigajoule of plasma energy, not fusion energy, plasma energy contained. I was last week at the International Energy Conference in London, and there were also many private companies, and there's really a buzz. At the moment, the companies have acquired even 6 billion euros. And there's companies both in the inertial fusion and the magnetic fusion, so it's really good to see this chemistry. But many of these companies, they work on concept improvements, and they're not working on the materials. And so if they come with promises that in 5 to 10 years we have a working reactor, I can't believe it myself, because they often ignore how to breed tritium and how to work on materials. Fusion is only not giving nice results at the end. The medical resonance imaging has quite profited from the superconducting cables we developed for ITER. Also, the cockpit of the Airbus is made with techniques we developed in the Netherlands for ITER. This is explosive forming, where you really bring this thing with an explosion in shape. And also all the remote handling which we have done in JET is used in many fields, even in medical surgery. So fusion is moving fast. I said it's clean, no CO2 emission, safe, no meltdown, no chain reaction, no long-lived waste. We can reuse the materials after 100 years. It's baseload, you don't have to wait for the wind. A small footprint. This picture shows the design of a Chinese plant. This is a plant which delivers 2 gigawatt electric. That's for a city of 5 million people. And if you want to do that with solar cells or windmills, you see the numbers you need. And there's abundant fuel. This plant, to basically give the energy for all these people, all these 5 million people, would need in the order of 500 kilograms of fuel per year. So partly deuterium, partly the lithium. Let me end with a famous quote, or quote from a famous scientist, Stephen Hawking. You probably all know him. His very last book he wrote shortly before he passed away was Brief Answers to the Big Questions, published in 2018. And the very last question he answers: what world-changing idea, small or big, would you like to see implemented by humanity? And his answer is, this is easy, I would like to see the development of fusion power to give an unlimited supply of clean energy. And who is better to follow? It's really a great quote. Ladies and gentlemen, I thank you for your attention.
Very nice. A very good reference at the end.
Yep.
Question, please.
It seems ludicrous that you're building this fantastic device, billions of dollars probably to develop it, and you're still using it to generate steam to turn turbines to generate electricity. Is there some future way of doing it so that it's more direct in terms of
Yeah, there's this group which look in other ways to convert the energy which is in the plasma into electricity. But for let's say the tokamak and the first generation of tokamaks, we very much let's say rely on the heat, which we get, let's say, for free because we need to breed the tritium. And so the blanket will be hot anyhow, and in that sense it's kind of you get a heat for free, and we use it to drive the turbines. So why not? But there's groups, Helion Energy in the US, for instance, is looking into different ways in getting the energy out of the plasma.
We have time for another question. Yes, please.
Yes, so two questions in one, okay? So the one question is the time scale. So if ITER DT operation is 2037, do you think you have enough time to start commissioning a demo in, you have about 7 years? You know, considering an if the ITER took something like 20 years to build, and do you think that high temperature superconductors and high field tokamaks can change the plans and go into something smaller if Commonwealth fusion system is successful in their experiments?
Thank you very much for these questions. Very, very interesting questions and very good ones. With regard, yes, we in our old roadmap, and the picture is from the old roadmap which we published in 2018, we have a sequential approach. We wanted to test the tritium breeding modules in ITER. And then automatically, if you don't change anything, this will now change in the 2040s, and then you can only test the blankets for demo, which would mean that you can build demo in the 2050s and maybe have it operational 2060. So we are trying now to look into parallelizing the work which we do on the R&D for demo to ITER. Very important is there to test tritium breeding by other means. So we are looking into a small volumetric neutron source where we can test the tritium breeding and also test the materials to do that on a faster time scale, such that we still can follow, let's say, for demo 45. It's enormously optimistic, I must say, because you need to find a site, you need to work on the legislation. So if you ask my meaning after 1 or 2 beers in the evening, then I will give you the true answer, but I like to be optimistic. I think we can do it, but everything should come together. We need politicians which give support. Ideally, you need like a Manhattan-type project to do this. Now, your second question, we did scalings for our demo, because ideally you want to have a small demo because it's less costly. The higher magnetic field doesn't give you a smaller machine, and that comes from, if you just follow the physics only, a higher magnetic field allows you to compress a plasma at higher power density in a smaller volume. Where nature hits you back is that the forces between the magnets, they go with B squared. So if you double the field, the forces go up with a factor of 4. And we don't have yet the structural components to hold the magnets together. So I really am very eager to see how Commonwealth and also Tokamak Energy in the UK are going to do that. But also with these higher fields, the stainless steel structure, if you would use stainless steel, gets more bulky and it pushes the plasma outward. The second problem with a small plasma is that we try to keep the diverter plasma away from the materials. So it's like the diverter flame front, which is like the blue line in a candle flame, which is the hottest part. You don't want that touching your diverter. We have very good control techniques there, but sometimes it goes wrong and we get reattachment. In a very small plasma where you get reattachment, you might basically make a hole all the way till your cooling channel within milliseconds. So the bigger plasmas are there more forgiving, and for this reason we are working on a demo which has a major radius of 8-9 meters. Personally, I need to see, maybe there's breakthroughs in materials, etc., that we can go to smaller, but I'm very skeptic whether that's possible.
Another question?
Thank you very much, María Garta from Techniker Spain. I would like to ask you, you comment that this technology is causing zero emissions, but it's necessary to heat at very high temperature. and then, but heating with this temperature, you can reach much bigger energy. That means that you close the loop in terms of reusing the energy that you have used at the beginning?
Yeah. Well, at the ITER will be roughly 50 megawatt in, 500 megawatt out. And if you look in how much electricity ITER uses to get these 50 megawatt, I think ITER is roughly break even if you compare fusion power versus the input power, but no electricity. In demo, we have in the order of 1.5 gigawatt fusion power versus 500 megawatt electric power. So about 1/3 of the power is the output. So the power in the reactor is much higher, the recirculating power, than the power out, but we can make it work so that we really have net electricity generation.
In the final question.
Thank you very much.
Brief.
Yes, 4,000 researchers. Can you comment on the expertise of these researchers?
Not individually, but what I can say and what we know is now fusion is really becoming a hype because also the private companies, they're taking away many people. Where we're really scarce is in nuclear engineers. Also because nuclear fission was not so popular, so many universities stopped their education in that area. We really need to again, let's say, bring this up, work with the universities, and yeah, get them involved. I forgot today. Yeah.
Yeah. Okay. Well, then we thank you very much for your talk and for your effort to come to Madrid for this occasion.
And sorry, I put a slide because I now need to run to the airport again. But
thank you, Professor. Your taxi is waiting for you.
There, so thank you very much. So
you're welcome.
Yes. And I have to apologize because we didn't told you that we were changing the program, so I apologize. Professor Tony Donet is in Eurofusion. He's going to, Dr. Campbell, quantum imaging of ionizing and ionizing radiation.
So this is a presentation which is not going to be about fusion, but there will be some applications of fusion in the.
But it's not too bad to have a rest from time to time.
Yeah. I wanted to say now for something completely different, but I don't know if you get the context. So basically, it's a presentation about quantum imaging of both ionizing and non-ionizing radiation, and then some applications. It started off at CERN, so I'd like to introduce what we do at the CERN LHC experiments, and for those, why we use hybrid pixel detectors, and then describe the the TimePix and MediPix chips, which is a project I've been running now for the last 25 years, and then afterwards explain how the TimePix chip is used to demonstrate radiation in classrooms in space, and how the TimePix chips are also used in laser plasma experiments. So CERN, for those of you who don't know it that well, is the world's biggest physics research lab. We have 23 member states, 19 associates and 48 non-member states involved in experiments. We are about 2,500 staff members who are mostly applied physicists, engineers and technicians, and about 12,000 users who come from different countries to do their research at CERN. Our annual budget is about the same as a large university, basically, 1.4 billion euros, more or less these days. And probably CERN's biggest impact on the world outside of its core mission has been that Sir Tim Berners-Lee invented the World Wide Web. So here's an image of the CERN site. Basically, we have a series of accelerators which are underneath the ground. So there's a small one here where we start accelerating protons, we inject it into the larger accelerator here called the SPS, and then finally into the LHC, which is the largest particle collider in the world. And the airport of Geneva runway is there just to give an idea of the scale. If we look nearer underground, this is not to scale in depth here. What we do is we send bunches of protons in one direction and in the other direction into the LHC, and then we accelerate them to as close to the speed of light as we can achieve with the present systems. So in order to basically to turn the protons around the corner, we have to cool the entire magnet complex to 1.8 Kelvin, which is colder than outer space. So in these particles, they come in bunches of 100 billion each. They're separated by 25 nanoseconds in counter-rotating directions, and then they collide every 25 nanoseconds. But of the 100 billion particles which interact, only about 20 or 30 actually do interact, because the beam size is 16 microns. But if you scale up the size of a proton to, say, a marble, the nearest marble to this one in this room would be in Barcelona. Okay, so the beam is small, but it's really big in terms of the size of the protons. So essentially what we're trying to do is collide those particles and then see what happens. If you look at the detector, the detectors are, this is the Atlas detector, the first version of it, so the protons would come from the right and from the left. This is a physicist here, just to give an idea of the scale of the detector. And basically the particles collide here, and then the debris particles fly out through these big detectors. And if I take just one segment of that detector, you see what happens. So the particles are created right in the middle of the detector. They go through these tracking layers, which is where my detectors are, and then they have two large sets of detectors called calorimeters, which try to stop the particles, non-charged and charged particles. And then finally, at the very outside, there are these muon detectors, so muons don't stop at anything. Now, a signature that you've had a good head-on-head interaction is that you have muons going in opposite directions. And if you look at the scale of the experiment, you can imagine that it takes much more than 25 nanoseconds to make the decision that we had a good interaction. So basically what the tracking detectors do is we kind of photograph every interaction every 25 nanoseconds. We wait for the decision on the trigger, and then we select, well, a few hundred frames later, the frame which we're going to read out for analysis. So it's basically a huge kind of needle in a haystack operation. The tracking detectors really in the middle are all now made of these hybrid pixel detectors. And a hybrid pixel detector is the topic of my subject of my talk today. And basically that is a CMOS readout chip. So this can be made from any standard CMOS process. It's divided into individual channels, and those channels are connected each to its own individual sensor element. And the sensor elements are an array shown here. This is typically high resistivity silicon. So what happens is that you have charged particles traversing the whole thing. They deposit charge as they go. This creates a pulse because there's an electric field here. So the electric field accelerates the particles towards the collection electrode, and then the signal here is processed in the readout electronics. Now, it's this very intimate contact between the sensing element and the readout electronics, which means that the precision of detection here can be very high. So the noise, typically in the front-end electronics here, even at very high shaping times, is something of the order of 100 electrons. The quantity of energy deposited is about many thousands of electrons. And so if you set a threshold at, say, 600 electrons, you're going to detect every passing particle, but the pixel is never going to react if there's no passing particle. So you have a clean imager. So that's the reason that hybrid pixel detectors are used at LHC. This is an example of one of the systems in LHC. It's the Atlas pixel detector, the first version of it, which would see 3 cylinders of pixel detectors around the interaction point for a total of 1.7 square meters of silicon, which is a lot of silicon and 800 million channels. And the individual chips look like that. There's nothing much to say about that. It's 18 by 160 pixels. And the modules are put together with a single piece of silicon here connected to 16 little chips, which are underneath there. And then all of that is read out through this Kapton foil on top of the detector. And that's just a picture of the technician assembling one of the layers of the Atlas pixel detector. So you can see that one of those things I just shown is here. And you have many of those which make up this detector. Now, if you look at a typical event triggered and analysed afterwards, this is the kind of event which we get at LHC in the first run. And what you can see here is that the physicists have been able to reconstruct every one of those 20 or 30 interactions which took place within a 25 nanosecond interval, and basically make sense of all these tracks here. And that's possible because of this noise-free imaging of the tracking detectors and the pixels. And before the Higgs boson announcement was made, probably a few thousand of those individual interactions were tagged as having created a Higgs boson. There were about 10 to the 15 events had taken place. So you can see that when I said a needle in a haystack earlier, I meant a needle in maybe a mountain of haystacks, something like that. So pixel detectors were developed for LHC for solving that problem of basically pattern recognition, if you like, in those detectors. At the time we were doing those, we started saying, well, what about applying that detection principle to other technologies? And that's what I'm going to focus on today. And so we founded these Medipix collaborations, which I'm going to describe later, and focus on the TimePix chips. So these Medipix collaborations started in 1999. The fourth one started in 2016. There's about 40 members. All of those members are academic institutes. There's no commercial entities there. And those people determine the strategy and which chips we're going to develop for within that particular experiment, within that particular collaboration. And this here shows that even though we've had basically the specifications made by our scientific members, we also make chips which are useful and can be used in other fields. So this is a list of the companies who have signed commercial agreements with the various collaborations. So the Medipix 2 collaboration, we made 3 chips, the Medipix 3 collaboration 2, and the Medipix 4 collaboration 2 chips. And you can see that probably we've generated a few hundred jobs or so in these different startups in this kind of cluster of companies around the Medipix collaborations. So coming back now to my original picture, here you see the hybrid pixels are typically with silicon whenever you have to see charged particles like this one here. But if you try to do, say, something like X-ray imaging, and you want to look at an X-ray which has come through someone's body, it is an energy of 60 keV, and that will pass straight through the silicon. So the big advantage of hybrid pixels is that you can switch out the pixel sensor from silicon to something which is more absorbing, like cadmium telluride or gallium arsenide. And so basically the flexibility of switching sensor materials from application to application is possible. Now, one of the limitations, as I mentioned earlier, is that the threshold for detection here is something like 600 electrons, which is set by the electronic noise. But there are other solutions. By combining the same chip with something here called a GEMPix, it's possible to reach lower energies. So in this case, a lower energy photon, let's say 1 keV photon, generates a few 100 electrons in the gas. Those electrons are then drifted down in an electric field to 3 planes of what are called gem foils. And those are just foils which have a high electric field across them. And there's an amplification of the charge throughout each of these fields. And then the charge cloud is just drifted directly onto the chip, just as it would be. So the chip basically sees a charge cloud as if it were a semiconductor detector. So let's look at the TimePix logic. Basically, we have this bonding pad here, which is connected to the input of the pixel chip, the pixel sensor. At the output of the preamplifier, we have a pulse, shown here as 4,000 electrons, a threshold of 600 electrons. You see here this good separation of threshold noise, so no noise hits. And then from the output of the discriminator, which is shown here, basically, so this is the preamp output, this is the discriminator output, you can decide what you're going to do with that pulse. So one thing you can do is just count the number of hits. So you have a kind of camera logic. You open a shutter, count how many hits are above threshold, close the shutter, and read out. But then you can do other things like measure the arrival time of the particle, which is shown here. So you count clock ticks from when the discriminator fired to when the shutter closes. Or you can measure something like time over threshold, where you measure the number of clock ticks while the discriminator is above threshold. So in that case, you get a measure of the amplitude of the deposited charge. So those are the 3 operating modes of the Medipix 1 chip. The chip can be integrated on a CMOS, a USB readout system like this one here. So it becomes very handy. You plug it in. If I could have used my own PC, I would have demonstrated detecting radiation live in the room here. But in any case, basically it's very handy and easy to use. The first system was developed by our colleagues in Prague, the second by their spin-off company. And if I opened that shutter at sea level, maybe roughly here, you get this kind of background radiation. So basically, this is the 256 by 256 pixels, and basically you see there's a couple of hits coming from radiation in the concrete of the walls of the room or something like that, or from cosmic background. If you take the same image on a plane, 34,000 feet, you see that when we fly, which probably many of us do most of the time, you see that we get quite a bit more radiation up there. And remember that this silicon sensor is only about 500 microns thick. So it's 1 by 4 centimeters squared, sorry, 1 by 1.4 by 1.4, and about a few hundred microns thick. Now what you can see already from these trajectories here is that, for example, here we have a squiggly track, that's probably an electron. Here we have a straight track, that's probably a muon. Here there's a kind of thicker track, which is probably a heavily ionizing particle. And here there's a kind of blob, which is probably an alpha. So just by looking at the shape of the cluster and looking at the amplitude of the charge deposited, you can distinguish one particle from the other. And if you know that information, you can then start to do other things with it. Now the first thing we did with it was we said, okay, let's put that into classrooms. So most kids don't understand what radiation is when they leave school. They've never seen a particle. With this detector, you can put that in the classroom. You can put an alpha source on top of the sensor. You'll see blobs. A beta source, you'll see squiggles for electrons, or a gamma source, and you'll see dots. So you see individual hits. Are they all physicists or engineers? I'm coming to that. So this lady who was a physics teacher of the class, she is a very charismatic person, and so she set up something called the Institute for Research for Schools in the UK, and then they tried to track their success over the years with the comparing the IRIS schools with non-IRIS schools. And in the male students, they found that over this kind of 3 or 4 year period here, the percentage change in the interest of boys for going on to study engineering increased by 38%, but for girls, the percentage of interest was significantly higher than for boys. But of course, the absolute numbers were still quite a bit lower than you would like them to be. But it just shows that giving teenage kids an exposure of the usefulness of physics at that age can sometimes be a moment to kind of keep them interested. And this is a more recent example in the Barcelona region of a girl who's using the same device that I have on the desk here for measuring background radiation in her local environment. That's the same chip. It's on the space station. That was taken a long time ago, probably about 2012. We've had about 6 of those chips running continuously since 2012. I think in total now we have 10 chips up there. So NASA were very happy with that. This is a 4-second exposure over the South China Sea, where you see again the kind of characteristic shapes of interactions from different particles. The same 4-second exposure over Argentina shows that, which probably most of you know as the South Atlantic anomaly. So you can make a map then using the position of the space shuttle, the space station, with the radiation dose to the astronauts, and very well see the influence of the South Atlantic anomaly. NASA have basically taken this as their baseline dosimeter. So they flew 4 of our chips in the Artemis launch last year. 3 were as a radiation monitoring device, and 4th was part of a small experiment. And these are just some very fast results from this is the moment they passed through the Van Allen belts just after their launch, basically, where you can see the counts on a logarithmic scale going up enormously. And then this is where they were near to the moon, and here you can see the influence of the shadow of the moon on the galactic cosmic background on the spacecraft. And they're basically foreseeing to use the chips in many forthcoming runs, and in fact we're quite excited because we're hoping to have chips on the lunar surface one of these days. So in the Medipix, the TimePix chip, we were detecting the particles with an arrival time of something like 10 nanoseconds. If you look at one of our sensors, it takes 25 nanoseconds or even 50 nanoseconds for the charge to drift. So we asked ourselves, what could we do here to basically enable us to distinguish that hit from this hit? And basically what you can do is, if you have a better timing precision at the pixel level, in this case 1.6 nanoseconds, you can really see the drift time of the charge in the sensor, and therefore make a kind of semiconductor time projection chamber. So it's a time projection chamber, not based on gas, but based on semiconductors. And that's an example of a muon at one of our test beams at CERN going through a 500 micron thick sensor and kicking out a delta electron at the same time. And it's been nicely reconstructed. But I was told that the subject of the session was fusion, so I did some searches along the collaboration members to see who had been working with fusion plasmas. I came up with just a couple of examples here to finish off with. So here, this is quite nice. It's an experiment carried out by some colleagues in the Czech Republic, basically, but in China, I think they did the measurement where they used this 200 terawatt Klapper laser focused to 4.5 micron diameter on deuterated polyethylene nanowires. And basically what they've done here is they've taken the Timepix 3 chip, and instead of having naked silicon there, they put some absorbers on top. So in one part of the chip they have lithium fluoride, which is able to detect thermal neutrons because there's a reaction where thermal neutrons are absorbed and kick out alphas or tritium particles. And then there is a polyethylene area on top of the chip where fast neutrons are converted into recoil protons. And using this pattern recognition I mentioned for the other applications, you can well distinguish one from the other. And this is just a very, very fast summary of what that paper says. But basically, on the area of the chip covered with polyethylene, they were able to very nicely reconstruct 8 of these recoil protons out of the 81 shots which they took during the exposure time. Switching now to another application in fusion, here based on the GEMPix detection system. As I said, the advantage of GEM compared with the semiconductors is that you can get some amplification in the sensor, so you're sensitive to lower energy photons. And this is what they did here. They looked at the low energy photons coming from a setup at the Vega 2 experiment, where the GEMPix is here and basically looking at the target and trying to reconstruct the number of low energy photons which can be seen there. They had a chip, which a GEMPix, which was composed of 4 chips, one without any filter on top, 2 with a 100 micron filter, and 1 with a 200 micron filter. And then they looked at the time over threshold information from the different quarters of the chip there and reconstructed those histograms here. They made a ratio of the 100 microns and 200 micron filters to the naked part of the chip, and basically what they were able to determine was that they could measure the soft X-rays and show a good match with the laser target interactions, and also the use of the filters allowed to demonstrate a correlation of the signal with the plasma temperature for these different shots which they were using. So basically it's used as a diagnostic tool for these experiments. So in a 20-minute talk, I can't possibly cover many of the applications that we've treated over the last 20 years or so, but probably the biggest one is spectroscopic medical imaging. So because we detect the photons one by one, we can determine their energy and then record them as such, and that gives a kind of extra dimension to X-ray imaging in the medical world. It's now coming into commercial use, but there are tons and tons of other applications which would be too long to go into here. So to conclude, hybrid pixel detectors were developed as tracking detectors for the LHC and made an important contribution to the Higgs boson discovery, and they're still used in these experiments. The Medipix 2, 3 and 4 collaborations have taken the technology to new fields. Timepix chips have been actively detecting background radiation in school classrooms and in space. The Timepix 3 can be combined with various absorbers to detect fast neutrons at plasmas. It can also be combined with a GEM detector for soft X-ray imaging at plasmas as well. And I think one of the themes of this workshop was the multidisciplinarity, and I think our collaboration really represents a true multidisciplinary community, where you can see that basically by designing one set of ASICs we can address multiple applications. So thank you for your attention.
Questions?
On these detectors, how often do you have to replace them? How damaging are the particles to the actual detector?
So the detectors used in the CERN experiments The ASICs can be designed to be extremely radiation hard, so they withstand gigarads of ionizing radiation and 10 to the 16 neutrons per square centimeter or so. The Medipix and TimePix chips have not been designed with the same techniques in mind, so they don't have the same radiation tolerance. And in fact, we don't measure it, because if we did measure it, we'd be subject to export controls. The truth is that if you measured this phone, it would be radiation hard as well, but no one does, because that would be subject then to export control. So we don't know the number, but it has been used in many radiation environments. Well, on the space station it works continuously, and it doesn't seem to have too many problems, let's say.
Another question.
Thank you very much. Excellent presentation. Very, very, very pleased. Can you comment on the application that you, in one of the last slide you have mentioned, quantum entanglement experiments?
Yes. Yeah, so I'm not an expert. So basically for quantum entanglement, it's usually done using some photon conversion system. So we have a commercially available system from one of those commercial partners I mentioned called TimePix CAM, and there they take a visible image, so single photons. They have a multiplication system for visible photons based on microchannel plate. So they turn individual photons into pulses of photons. Those photons are then sent to the chip and detected just like we detect any other particle. And there have been a number of experiments using that single photon sensitivity in quantum entanglement, but I don't know the details of those experiments, but I can certainly find that if you're interested.
Okay, thank you.
Well, if there's no more questions, we thank again the speaker for this talk. Now we are going to have a phase transition, in the sense that the chairman was going to be replaced by chairwoman. So I take the chair for Professor Santa Maria.
Thank you, Miguel Ángel. Thank you, President, and thank you, everyone, for your attendance to our symposium. Now the next speaker is Professor Manolo Perlado, please. And to introduce him is just to introduce the history of nuclear fusion in Spain. I'm going to do it very, very fast, but to start by telling that late in the 70s, Professor Perlado, is presently Professor Chair of Nuclear Physics, President of the Institute of Nuclear Fusion, and during the 70s, he's co-author of the first non-classified computer code, time-dependent coupling hydroradiation, and Monte Carlo discrete ordinate neutron. In the beginning of the 80s, he is pioneer of full calculations of neutronics magnitude in inertial fusion energy reactors and co-author of the first version of a CAP code, totally implemented as basic code for licensing in ITER project. End of the 80s and 90s, in collaboration with Lawrence Livermore National Laboratory, first in doing atomistic simulation of radiation materials damage, developing the multi-scale modeling for fusion in Spain, is co-designer of accelerator-driven systems in the 90s, together with Nobel Prize Carlo Rubbia. Lead of technology physics in a hyper-European project from 2007 to 2014, and presently is promoting several coordinated research programs at the International Atomic Energy Agency in inertial fusions since early 90. And Spain representative in the program committee for fusion since middle 90s. Professor Perlado, the floor is yours, and thank you very much.
Thank you very much, Nati. I love you. Too much. No, this one I have here. Everyone hear me? Yes. Well, now we will talk about energy. Tony talk about magnetic fusion energy. Ricardo talked about the principle of inertial confinement fusion. I will go now where we are in energy for an inertial confinement fusion. You hear before to Luca Volpe and Ricardo Betti about the point where we are now. We are in gain 2. NIF was proposed for gain 5 or 10. So we are approaching that. Some people is saying we really can arrive to a game 5. We will see, but this is the situation now. And you also heard to look about many different concepts that we have in addition to indirect drive, as Ricardo was presenting. We have direct drive, we have set pinch, magnetic pulse power analysis, shock ignition, and so on. So we have different ideas. Okay, so here is where we are. This is what you use it for ignition and gain in NIF. That's a laser of 2 megajoule at the third harmonic, 4 megajoule maybe in the second harmonic of neodymium laser, solid laser with a frequency of only 0.0002 hertz and an efficiency of 1%. So that means we have no possibility to make a reactor with that. So there is no energy from the point of view of commercial with that. Where we need to go? We need to go to something, maybe diode pumped solid state laser, maybe excimer laser, maybe ions with frequency repetition just in between 0.1 10 hertz. Lucas said this morning 10 hertz. Well, there are ideas that also represent to go to frequency of 0.1 hertz of the repetition of each one of the shots that Ricardo was commenting today. So that's one shot. We need at least 10 shots per second, or maybe 5, maybe 2, but in that range. And we need some efficiency larger than a 10%. If you have not that efficiency, certainly you have not the numbers to arrive to energy from inertial confinement fusion. So these are the numbers. Energy 0.1 to 10 hertz. Energy, depending on the idea, and you saw in my first slide that there are many different ideas, of several different ideas to do the same that NIF do this with indirect drive, but others from hundreds of kilojoule to 20 megajoule. Some people is saying, well, I will obtain a laser of 12 megajoule. Well, okay. Or indirect drive, we are in the range of hundreds of kilojoule. Peak power in the range of 100 terawatt, an average power up to 10 megawatt, and a number of targets, materials, and manufacturing problem close to 1 million of capsule per day. And this is the number, 24-hour, number of seconds per hour, and a repetition rate of 10 hertz. That means close to 900,000 targets. Well, I start saying something that I would like that Tony Donnet hear, but unfortunately he is not. Inertial confinement fusion, inertial fusion energy has a big advantage to make the research and development to magnetic fusion, which is the modularity. We, in principle, could research in one way the drivers, could be laser, could be X-rays, could be ions, but each one of those driving sources could be independently researched. We have a different scheme of illumination. You show, I don't know why it's not fast ignition. There are indirect drive, there is direct drive, there is fast ignition and shock ignition. I will not enter in the details. Ricardo talk and probably will talk tomorrow, and Luca also. We have different ignition scheme. We have the central hot spot and the non-central hot spot. Pulse power need to be there, and we have different chamber protection. So we have 4 elements, several elements that could be analyzed in an independent way and put together at the end to obtain the energy with those parameters. This is one capsule. Fortunately, Ricardo put in his view graphs this aspect, very critical. And I will not enter more in that. That's one capsule. You see that is a range of 1 millimeter radius with high density carbon outside, DT cryogenic in the middle, so about 50 microns, and vapor inside. This is a picture of, well, excuse me, an X-ray radiography of one of the target, and that was Ricardo mentioned before, and this is a materials problem. This is to detect that we cannot allow defects in the capsule. And another important point, people is developing the diagnosis to make that in a, let's say, procedure. There's a systematic procedure. So this is one comment that we have in problems. This is another problem. We know that the defects in the capsule are, we know now, because of NIF, we know that the defects in the capsule are very critical for arriving to the final ignition engage in the system. So that is solved partially because of this analysis of the defects in the outer layer that arrives to be manufacturing almost zero. But the full process we need to optimize. This is one example of what they did for targets in NIF. So you see, which is the time scale of the target manufacturing and the many different processes from the simple mandrel of silicon mandrel to the end when the DT is filled inside the target. So it's a long procedure that we need to optimize from the point of view of inertial confinement fusion if we want inertial fusion energy.
One at a time?
Excuse me? Yes, yeah. One side, yeah. And well, people is working in that. This is the positive way that I want to transmit you. The answer is yes. There are people doing that. There are laboratories doing that. General Atomic in US, Los Alamos in US, in United Kingdom, the Central Laser Facility in Rutherford Appleton Lab, in Fraunhofer Institute in Germany. So there are, and the Japanese also in the Institute of Laser Engineering. There are different approaches now to make a massive, because it's about 1 million per day. So we need a massive build-up of this target, where we are not in the point to say this is okay. We have holographic 3D printing, nano imprint, and origami folder of the target, and emulsion polymerization. So that's a challenge. That's a challenge for inertial fusion energy. A tremendous challenge. We have. I will comment about this afterwards. But about the laser in itself, Luca, I think, mentioned this morning, we need to pass from the typical solid-state laser now, which are with using flash lamps, very low efficiency, diode pumping solid-state laser. From the point of the optics, we need to pass from the present glasses to ceramics. So we have two steps there, which is material science, not only technology, but also science in that sense. So this is just to show you that people is doing that in Europe during the Hyper project that Luca mentioned this morning. That was in 2007 up to 2011, 2013. So it's recent, and Europe at least not using fusion funding, but using infrastructure funding. I want to remark this, was starting to make that in these laboratories. I will not enter more in this. And this is curious. What about, because remember that we have 100 pulses per second. So that means that the laser is shooting 100 times per second, and the target need to coincide with the laser 100 times per second. So the target need to be injected and made the coincidence with the laser. That technology already exists? The answer is no, but the people is doing that. And this is a clear experiment made by the Graduate Photonic Institute together with the Institute for Laser Engineering, making a shooting of targets at the rate of about 10 Hertz. They did in different frequency, and obtaining more than an 85% of the coincidence between the laser, of course, low energy laser with the target, which were injected in the system. Also in Europe, in the Hyper project, the Czech Republic produced an injector that could be working in that. Okay, so let me go now to other point where that Tony was talking before about the target, the chamber, and so on, which is another piece. Luca was talking about laser, Ricardo about the implosion. Now I will talk about the chamber, which is the position of the chamber. Well, the first thing which is curious is that the number of designs in inertial fusion energy along decades is much more than the case of the magnetic fusion confinement. So that's curious because magnetic fusion is the supporting this routine activity, but it's curious. So US did at least 15 designs. Of course, rough design, general conceptual design, but there was physics and proposal inside that unfortunately many of them were not progressing the research. Europe did. And this is 1982. Heibel 1 and 2 in Germany, together with the University of Wisconsin and our institute, that were collaborating in that European project in Germany. Libra, heavy ion design, and finally Hyper. And Japan has now 3 conceptual designs, which started essentially in the 90s with the Koyo reactor, the Koyo fast ignition reactor, and very recently the LIFT reactor. So people is moving in that sense. This is a table that I got from the draft that Luca mentioned this morning. Is a study. Ricardo was one of the chairman of this work, together with Tammy Ma from Lawrence Livermore. They were both really scientists in that. This is the TRL, is the technological readiness levels. So it's between 1 and 10. 1 and 10. The first 3 are laboratory. The 4 to 7 is more than laboratory, some technological development, and from 7 to 10 is very well developed. So this draft consider, as you see, that all of them are low than 5. So we know, of course, I am not agree with the. I'm sorry, Ricardo, I am not agree with this one, because chamber design and first world material, even that we need a lot of this of research, is not as bad. Is not as bad. But anyway, so you see that in any of the different proposals, laser indirect drive, NIF, laser direct drive, shock ignition, Luca, Europe, fast ignition, heavy ion, magnetic driven fusion, the numbers of the technological readiness level is low. Is in general low, less than 5, in a range of between 1 and 10. I will not enter more in this, but anyway, keeping in that. So why in the case of inertial fusion, the proposal could be, let's say, a little bit better than in the case of magnetic? From the point of view of the material damage in the first wall and other aspects. Because in the case of inertial confinement, inertial fusion energy reactor or chamber, we have a possibility that in the case of magnetic fusion, because of the magnetic fields, they have not. And the reason is that we could protect the first wall. We could protect the first wall that see the microexplosion directly with something. For example, a gas, as was proposed in the case of LIFE in US. For example, a thick liquid, so a jet of 50 centimeter downward lithium lead or flyby that protect the material of the first wall, and all the energy of the microexplosion is in the liquid, not in a solid or thin system. So this is one proposal. Of course, we can make drywall completely unprotected, but we have a real possibility there. Europe did the work, and I want that you know this. Okay, Hyper did the work. Conceptually, yes, no more funding. but conceptually we did the work. And we did the real design, considering the different materials of the first one, which was not tungsten, but nano-tungsten, because of the self-healing effect of the nanomaterial instead of the bulk materials. We consider reduced activation ferritic martensitic still in the system, and a full design. Maybe we need to check many things, sure, but there is a full design. Here you have, there are 16 sectors on the upper side, there is 16 sectors in the downside, there is a full design of the coolant flowing, which was lithium lead, and the velocities and the corrosion of the system using a specific material. And one interesting thing that now is rescued in Hyper Plus, the new initiative, is that by the first time it was proposed 3 different steps. We don't want to go directly to a demo or something like that. We have the ignition in indirect drive already done, but what I want to remark is that we propose something which is very simple in principle. So you see, there is no a high gain. It's only 20 megajoule. But this system has something critical, and they have something which is the repetition. We have no systems now that are repetitive to 10 Hertz, 1 Hertz, 5 Hertz in the energies that we need in our system. So it's very simple. Luca explained, in fact, this morning, saying what we want is something which is in the range of 100 kilojoule or less, or some kilojoule, but key aspect, it must be repetitive. It must be repetitive. So a second stage, which is the prototype, which is a 24/7 system, and finally a power plant. So Americans did almost at the same time, because life was 2007 to 2012, 2013, the same work. And why I put this view graph? The reason is, well, you see, is fully designed in that sense. So they really designed the different pieces that compose the reactor. We reduce activation ferritic martensitic steels. They use a flyby, which is a composed of fluor lithium in beryllium instead of lithium lead. But anyway, they did the work with the cooling system completely designed and so on. But I used this view graph for one thing. They were in some way clever in one thing. The idea was, I am not sure if in a short range I can use the appropriate materials in my case of gas and so on and so on. So maybe the materials really are completely destroyed in 2-3 years. They are not resistant more than 2-3 years. So which could be a fast solution? The fast solution is not coming from the science in this moment, because it will take more time. It's coming from the engineering. And what kind of engineering? What kind of engineering? Why? I said that we have a modularity in our system. Why not to change the chamber? Of course, we will see which is the cost. Okay? But why don't you change the chamber and put another chamber each 3 years? Each 3 years. So it's a solution using engineering, using a scale that the science will not arrive to have in the appropriate time, according with the expectation just now. Okay, so let me make a comment about magnetic and inertial, because everybody said, well, you have a problem with the laser, but you are solving. You want repetitive. The idea is going to diode pump sodium state laser or excimer, blah blah. You are making work in targets. You are making work in the chamber also, and why not in the chamber make an interchange between magnetic and inertial? Of course, we are ready to do that. In fact, we are doing now in the institute now, because we work in materials for inertial fusion, back magnetic fusion. But what I want to remark today is that not everything is the same. There are many aspects that are not the same. And then we need a program for that. Heat extraction, cooling and corrosion, that will be almost the same. Okay? The heat in extraction will be a liquid, fly-B or lithium lead. The corrosion need to be evaluated, but the system is more or less the same. Tritium breathing and handling. The system for not to breathe, but to manage the tritium that is produced and generate the target again and again and again. So, which is the difference here? The system maybe is the same, but inertial fusion energy, because the targets are only 1 milligram of DT each one of the pulses, we have less inventory than in the case of magnetic fusion. That is by sure. A structural material, the activation or the production of the short-lived radioactive waste in both cases, or the radiation damage of the material. Of course, we are very much welcome of the MIFDONES in Granada. That will be a good point for us, for European, in magnetic fusion and inertial fusion. But we have a very special point that I will remark now, which is the pulsed effect. Here we have an irradiation which is not continuous, like in the case of magnetic fusion, but an irradiation which is 100 times per second, 10 times per second, 5 times per second. That make an effect? The answer is yes, according to what we know now. And first world material, different intensities and time scheme. This is I will not enter in the detail, but this is how many particles and neutrons you have in a target explosion. You see that the neutrons average is not 14, MeV, is 10 to 11 according with our calculation in dynamic calculation between radiation, hydroneutronic. Which is the reason? The reason is that, as Ricardo said, alpha particles is the key point. But neutrons can leave you per neutron about 1, 2 MeV. Yes, 1, 2 MeV you can leave in the target, very much compressed because of the neutrons and many other particles. And these are the spectrum in the case of the charged particle: hydrogen, helium, deuterium, tritium, carbon, maybe tungsten. So these arrive to the first wall in spaces of some micron, some only 3-4 microns. They penetrate with those energies, and they arrive, and the pulse is deposited in the first wall in times of microsecond, between 2-3 nanoseconds. So this is very much different what you have in the case of magnetic. We are not sure if that will be effect, but we need to explore that. Maybe that is something different. And this is a computational demonstration that is true what we are saying. This is the ratio of helium retention in 1 tungsten first wall. You see here the continuous irradiation versus the pulsed irradiation. And this is the time deposited in the chamber. You will see that the pulsed irradiation, the pulsed helium retention in the first wall, in the tungsten first wall or nanotech first wall, in the case of pulsed irradiation, is a factor of not 2, 1.5, but something larger than you have in the case of continuous. And this is the same effect, but in the case of the neutrons. This is the vacancy, the concentration of the vacancy cluster versus time in the case of the pulsed irradiation. In the case of continuous, it's perfectly continuous. In the case of the pulsed, and that is each one of the pulses in your system, you see that there is a tendency to increase the number of defects produced by the neutrons in that pulsed system. And the reason is that you have no time for the annealing of the defects in the system. I am finishing, my friend. Well, we are approaching in the Institute different concepts. One of them is the use of the nanomaterials, nano needles. Another very interesting is what we did very recently is not not experimentally, only computationally, which is to use at the first wall protection hollow nanosphere. So this is tungsten, hollow. When the radiation arrives to these hollow nanoparticles in the system, these are the hollow nanoparticles, the helium starts to be located inside the hollow nanoparticles. When the pressure is very high, the nanoparticle is open, release the helium through the ground, the different boundaries of the system, and when the helium is released, the capsule closes again. So this needs to be proved experimentally, but this is quite interesting. This is Hyperplus. My good friend Luca talked about that. This is the program that we have for the roadmap in 10, 20, and 30 years. So you see there is a detail trying to develop the program in different areas, in the physics and technology, development of IFE laser technology, and material science, and the IFE community building. And these are my conclusions. First of all, I want that you realize that this is not new. There is a very large number of ideas and studies, much more than you imagine, in inertial fusion. In magnetic, I know that you know, but not in inertial fusion. Have been developed in physics for developing technology in energy fusion energy reactor. I always put physics for developing technology, not technology. Physics for developing technology. There is certainly a key role in nuclear fusion energy to be played by inertial fusion, in my personal opinion. It's still a long way to commercial power plant. We need development in all the areas that I mentioned, and we request very clearly that Europe provide to inertial fusion energy what they did not provide. I'm sorry that Tony is not here, but I will say him, that they did not provide along decades. Along decades. So the idea could be they need to provide in the same extent, or if not in the same extent, and half or something much larger than we have in now. Thank you very much.
Thank you, Professor Perlado. Thank you, Manolo, for your excellent presentation. I think we have time for a couple of questions. Please, John.
Thank you. Thank you very much indeed. It's been I mean, I'm not a physicist, but this has been a fabulous trio of discussions, and thank you very much for that. And it's very sophisticated physics for me anyway. And I think it must be even more sophisticated physics for the politicians of Europe. And I just wonder how do you sell this ideas, and how do you sell this technology to the politicians? I mean, I was talking at lunchtime, I think, to you, and we were talking about billions of euros of investment. I mean, how do you convince European politicians that it's got to be at that kind of scale?
Well, thank you. Really, thank you. I was member of Spain representation in Brussels for almost 3 decades in the fusion program, particularly in inertial fusion energy. Europe at that time gave us only what they call keep in touch program. There are many different positions, many different solutions to what you said. One is clearly political. There are countries that doesn't like inertial confinement fusion to be spread, and then even that is very clear that there is a very much different in between an approach, military approach or a civil approach. It could be make a difference. They don't like. But anyway, so it's a keep in touch. Which was the amount of the keep in touch? For all Europe, all the laboratories of Europe, about 2 million. 2 million. For all Europe, almost 10 groups that we were in Europe at that time. I'm talking about the 90s and beyond. When Eurofusion started, we presented programs to Eurofusion. We were very happy in the very beginning because we got 2 projects. I'm talking about how many, Luca? 500? 500,000? 1 million. 1 million. And now we have 2 more. 2 more. Very general. You know, we never propose something that let us develop laser repetitive. We cannot do that. They never will allow. They could allow us, what do you want to make? Plasma physics? Okay, not indirect drive, but please do that. Or magnetic, you know, please do that. Very good, but you know, this is nothing. We have real problems in technology that we could now go on, really go on. This effect of the pulses. We need something that make a difference between the pulses and the continuous irradiation. We never will arrive to that in this moment, you know? So a facility is what is not allowed. So when we success, not the only one thing, when we success in hyper, why in hyper? Because hyper was an S3 project, was a large infrastructure project. And then this is out of fusion. Then you want to make a preparatory phase for lasers, okay, you can do. For technology of the target, well, you saw there. We did, people did in Rutherford. Anyway.
I think we don't have, I think we there are 2 more questions, but I think we are very short of time.
Very short of time.
Okay, maybe we can talk afterwards with panel. Thank you. Thank you. I think we have now, well, after Professor Cabellos, we have our coffee, so we can talk wherever you want. In terms of finishing on time. Thank you very much, Professor Perlado. Manolo, thank you. In our last presentation of this exciting afternoon is coming from Professor Oscar Cabellos. Professor Cabellos is full professor in nuclear engineering at the Polytechnic University of Madrid. He is coordinator in several courses as Introduction on Nuclear Technology, Simulation of Nuclear Power Plants, and Nuclear Energy for the Energy Transition. He was working a lot of years in the Nuclear Energy Agency data bank as nuclear data scientist, and now is different committees such as Nuclear Science Committee and the Management Board for the development, application, and validation of nuclear data and code. He has written more than 40 papers, well, it's written over there, okay, in international scientific journals with more than 60 papers in proceedings and more than 100 contributed talks in workshop. The floor is yours, Oscar, and thank you very much.
Thank you very much. Thank you very much, Professor Carpintero. And thanks a lot for inviting me to give this talk, this presentation. As you said, I was working at the NEA. This is the OECD NEA, Nuclear Energy Agency, since 2014, 2017 in this international organization. It's very important to have this participation in an international organization. I will explain a little bit more. And also, I am in the academia. I am professor in the different courses. I have highlighted the nuclear energy for energy transition. This is very important. In our Polytechnic University of Madrid, we have this course more than 20 years ago. We explained the climate change basic physics, the impact of climate change, the mitigation, the energy, solutions, and so on. More than 20 years ago, with Professor Perlado, I have the honor to, I was your assistant professor at this time. So, but in our industrial engineering school, we have these courses more than 20 years ago. So I think I'm very proud of that. And now my talk is about the nuclear fission. Nuclear fission, the role of nuclear fission energy to a clean energy transition. I gave this talk to my students last week, so just to have more information about that. And I did a small survey for my students. And one of the questions before my talk is if they trust in the international organizations. 65% of my students says that, yeah, they are trusting the international organization. They believe that Greenpeace is also good for them. But also the pro-nuclear organization, World Nuclear Association, they said that, okay, this is very good information. But only 70% of my students agree that they trust in the international organization. After my talk with my students, 100% of my students agreed that international organizations can play a very important role for the community. So I hope that after my talk, you will see the same feeling. So yeah, this is very important, the role of nuclear fission energy. This is the first talk on fission energy in this meeting, this event. I think it's very important to know what is the current status of the 16 nuclear power plants, and a lot of recent activities and challenges of the nuclear fission that maybe probably you, most of you, or know that, but probably some of them will be new for you. So I will introduce these main activities for the nuclear community. The first one, I think, this plot is already seen in this event. This is the current temperature, surface temperature in the world since 19th century to now. In black, we have the data, the observed data, and here also we have the models, different models that simulate the behavior of the temperature, surface temperature in the world. But this is very interesting just to show this shadow area. This shadow area is that all the models, climate models, computer programs, says that the uncertainty is around 0.2 degrees Celsius. So the uncertainty in the models is around 2 degrees Celsius in the prediction of the temperature. So, and this is very important because when you see the uncertainty in the future, you will see that in the future we will have different here. This is the shadow area here. See, seems that depending of our emission of gas, CO2 gas, we will have differences between 1.5 degrees up to 6 degrees Celsius. So the uncertainty in the future is not in the models. The uncertainty in the future is in our human emissions. You know, depending of our emissions, we will have different degrees of uncertainties. And I think it's another important point here is what is our carbon budget? I remember that in one of the presentations says that, okay, we have to limit our increase, the temperature increase 1.5 degrees Celsius. But to achieve this value, our carbon budget is around 420 gigatons per CO2. I know that this is some uncertainty in this value, but please keep in mind this number, because this number is very, very important. 420 gigatons CO2 to achieve 1.5 degrees in the end of the century. And yeah, this is also very important. We now here in 2020, this is our emissions, but if we want to keep below 1.5 degrees, we have to reduce our emissions. And if we delay, we will decrease. Our greenhouse emissions must decline rapidly. If we delay, we have to reduce more rapidly. So this is very, very important to know what is the emissions and also this number. And this is the current status of the world. This is the annual change of CO2 emissions in the last 10 years. You will see that there is we are still increase the CO2 emissions. Here in the pandemic year, yeah, we have a decrease, but after the pandemic, we increase the CO2. But we cannot see a very great change in the CO2 emissions, and also in the CO2 intensity, the grams for CO2 divided by the energy. So yeah, we can see here that we can improve our consumption of energy, emitting less CO2, but we need more and more, because here in 2020 it's a very small change. So we have to do something else. Yeah, and this is the international organization, the International Energy Agency. It is one of the bodies of the OECD. This is the 2020 to reach the 2050 net zero emissions. They said, okay, it's good to know that the electricity and heating is the main source of CO2 emissions. And we have to decrease these emissions. And I will try to explain that nuclear energy can play an important role for the decarbonization of this sector, electricity and heating. For 2030, we know that the electricity and heating should be reduced to this value to reach 2050 at zero carbon emissions, but there are other sectors in the world that we have to reduce. This is very important. Now for 2030, we are working with the technologies that are in the market now today. But for 2050, I don't know if the current technologies or the technologies that we are proposing are working or not. So probably I don't know, but what happens if these innovation technologies will not deliver the expected results? So I don't know if we can take this risk. So let's try to have more information about that. And now let's try to introduce the current status of nuclear power plants. Here is the nuclear power plants. This is the IEA website. I took the data in last week. So in total, we have 411 nuclear power plants. It means that this is around 10% of world's electricity is produced by nuclear fission energy now. And this 10% of electricity, if you recover all the electricity produced by nuclear power plants since 1970s to now, we have avoided 66 gigatons CO2 emissions. Remember, 420 is our budget, and we have avoided 66 gigatons for the all years up to 2021. Every year, nuclear fission avoid 1.6 gigatons per year. So I think it's a good number. Okay, we can avoid nuclear fission, but this is the data. In total, we have 30 countries producing nuclear power, electricity with nuclear power plants. And in total, I think it's very important. Today, we have 58 nuclear power plants under construction. It means we have concrete, steel, in a site, and we have in total 58 nuclear power plants. Most of them are in China, almost in India, 50%, but we have also in the US, UK, France, and Finland. So, okay, we have different nuclear, this is I think it's a very good number. But if you see the age of these nuclear power plants, this is also a very interesting plot. Here we have the age of different nuclear power plants, or for the 411 plants, and the average age is around 32 years. So this is the maturity of this nuclear energy. So if the design life is 40 years, we are almost at the end of the life of these nuclear power plants. But okay, let's try to explain that. This is the 32 years is the average value. In total, today we have more than 100 nuclear power plants operating with more than 40 years. But the idea is that why not go to more years, 60, 80 years in operation? And this is why I want to demonstrate that this is possible. So for nuclear fission, there are different challenges. I will try to summarize the long-term operation. How can the nuclear power plants operate more than 40 years? The flexibility of nuclear operation, the accident-tolerant fuels that increase the safety of these nuclear facilities, and also the potential role of nuclear energy for other applications, not only electricity, and also some ideas of the nuclear designs, etc. So first is the long-term operation. I said that the design lifetime is 40 years for a nuclear power plant. But okay, this is the safety performance at the first year of a nuclear power plant. This is the safety performance. We know that after 40 years, there is a deterioration. You drive a car, and you know that your car deteriorates with the time. But it's the same in a nuclear power plant. We have a deterioration with materials. Materials aging is deterioration, so that safety performance will decrease. But we have replacement. We have technical progress. We have operational experience. We have operators that have experience with 40 years operating the nuclear power plant. So this means more safer operation. The governing framework, and also the safety upgrades. So in total, this OECD report says that after 40 years with long-term operation, the safety performance is much better than at the beginning of the nuclear power plant. So we can operate safely these nuclear power plants after 40 years. And also, this OECD report says that long-term operation is much cheaper than other energies. If you compare the long-term operation, nuclear long-term operation is much cheaper than renewables, and of course the new nuclear energy, but long-term operation is something that we have already in the community. So it seems that this is something that we have to keep in mind, that the economical point is also very important, and also the security of supply energy. And the last point is the CO2 emissions. Okay, if we extend the life of these nuclear power plants after 80 years, we will save 49 gigatons CO2. So this is around, remember, 420. 10% of the emissions are avoided if we extend the nuclear power plants up to 80 years. Okay, so this is something that we are in the market, so this is something that we can discuss. The second point is the flexible operation of nuclear power plants. Here in Spain, we think that nuclear power plants cannot change the power. It's absolutely is not true, because in other countries, in Germany, you can see here different nuclear facilities in Germany. In the past, they can change the power in one day, and they can change 50%, 8%, 100%. Yes, the change is possible. So you can accommodate the production of energy in one day and in 1 year. This is a French nuclear power plant. This is the change in the power. So they can accommodate renewables and nuclear to produce the electricity that is demanded by the people. Okay, so this is the flexible operation is very important. So, but you have to do with nuclear reactors that are with the control system that is possible to do this operation. The third point is accident-tolerant fuels. We know Fukushima, but all the engineers, I remember in our nuclear power plant program in the academia, we know that Fukushima, the disaster was already known, because in Fukushima, after the Fukushima disaster, tsunami, they have not a way to remove the heat of the fuel. So we know that the zirconium with water at high temperature will produce a lot of hydrogen. It is well known. So we know that this problem is well known by the community. But this is the problem. How can avoid this chemical effect with zirconium? So in the 20 years ago, more than 20 years ago, the designer, the nuclear designer, started to change the concept of the fuel assemblies. Try to solve and trying to change the uranium dioxide and also the zircaloy, because they knew that this is a very potential problem in the fuel. So they have developed accident-tolerant fuels. Accident-tolerant fuels that can remove this issue with the fuel. For instance, just coating the zircaloy with chromium, and thus remove the problem with the hydrogen. Or change the zircaloy with another steel or with another material, silicon carbon. Or change the uranium dioxide with a better fuel assembly. For instance, using the doped uranium dioxide with different molecules, or nitride fuel, or silicium uranium, triso. So there are different changes in the community that we can introduce in our nuclear power plants to improve and to enhance the safety in these nuclear facilities. But probably nobody knows about that. So this is really a pity. Okay, so and here just a few comments about the new designs that now in our countries we are operating a generation 2 nuclear power plants. This is the generation 2 nuclear power plants designed in the 70s. But we can do better, and we are doing better now because we are now working with the generation 3. Generation 3 means that in these nuclear facilities you have 3 days with no human action to keep the safety of these nuclear power plants in an accident. So 3 days with no action. And we have here the AP1000 and EPR, and we have already built few facilities, few nuclear power plants based on this generation 3. So we have several in China, in the US, in Finland. So EPR and AP1000 are already constructed, and they are demonstrating that the possibility to enhance the safety. And here we have generation 4. Generation 4 is the future. We are still on the paper, but generation 4 means that we can improve even the fuel performance and so on and so on and so on. Enhance the safety, minimal waste, and so on and so on. If I can say something about the short-term future of nuclear energy, fission energy, I would say that probably the small modular reactors are the key. Why? Because there are a lot of countries that cannot accommodate 1,000 megawatts, electrical megawatts. But they can accommodate just a small reactor with 100 megawatts, electrical megawatts. So there are small countries that are trying to see if these small modular reactors can play a very important role for these countries. This is a small nuclear power plants. Below 500 electrical megawatts are modular. So it means that we can build these small modular reactors in a facility, and we can transport this reactor in a truck to the site. So this is, and also to improve the safety. And another important thing is that we can produce electricity and heat. And this is very important for the nuclear fission. This morning we said something about the heat. This is very, very important. Yeah, this is very important. We can produce heat in these facilities up to 800 degrees Celsius. Okay, so we can produce electricity and heat in the same facility. And this is very important. The nuclear energy can produce electricity, we can produce heat, we can produce hydrogen, and this is something that this is not strange. For instance, we have produced heat and electricity to produce desalination, and there are Japanese nuclear power plants that are working in this way. So nuclear energy and nuclear reactors can play an important role to produce electricity, hydrogen as another vector of energy, and also another kind of energies as heat. So the nuclear energy is a low carbon source that can produce electricity, and for the zero carbon hydrogen I think is very, very important. And regarding the cost, cost is very, very important. If probably the cost here is the levelized cost of electricity. This is the common way to compare different sources of energy. But this report, this OECD report, says that okay, the cost of energy is important, but you have to take into account also the green level cost, the social and environmental cost, to have a very good view of the total cost of the electricity. So this is very important. How can include in this cost? And here is a very nice plot. This is just my last slide. This is because here this is the carbon emission, the total carbon emission, and this is the decarbonization share. So here we have renewables, only renewables. Here we have only nuclear, and we can mix renewables and nuclear to decarbonize the sector. And here is the cost of the energy, the cost of the energy. So we have here now, this is the total cost of the energy. We can hear the value. This is okay, probably this is just one country, but this is the country that we have here now, and we can evolve to 2030 change the sector with renewables or keep another source of no-carbon emission as nuclear. So we can, in 2030, we can stay here, and the cost of the energy is very close. But if we move at 2050, this is the, at least, I don't know, but this is the OECD report says that the total cost with renewables will be much, much higher than other kind of mix of energy. Okay, so this is just a very, very, also very, very interesting results. I have also this slide, I think it's just to have different points about pros and cons of nuclear fission energy. Safety is very important, but please don't confuse. Risk and damage is different. Okay, damage is very important, but the risk of depends on the probability of the accident. So we have to build confidence in nuclear power. I know that this is very difficult with accidents, but we have to be careful that risk and damage for the nuclear energy fission and for other sources of energy is very, very important. And my last point here, I don't want to spend more time, but the energy transition is not free. It will have a cost. So I think, please also keep in mind that any proposals have a cost, and yeah, this is also the last slide. The conclusion is that thanks to this work by the OECD, IEA, other international organizations, we have probably a better picture of the problem in the future for the decarbonization. The decarbonization pathway is not easy. It's not only one way. We have nuclear energy. This is a possibility. Other countries say, okay, we are only working with the renewables, but we have in the market all of this to fill in this puzzle, and nuclear energy can be part of this puzzle. There are a lot of uncertainties and technology risk, and also this is very important to take into account that this uncertainty and technology risk can also play a very important role. And as I said, nuclear fission technology is already known, well established, and if we have the opportunity, we can continue working in this sector. So thanks very much, and if you have any question, I will try to.
Thank you, Oscar, for your very nice presentation. I think we have time for a couple of questions. I said not a couple of questions, and we'll have one question, but I think that now we have time for 2 questions, please.
What do you think is the main reason why, especially the Western country, and talking about specifically the United States, is not building many nuclear power plants anymore? My take is that the capital cost is just too high, and the modular reactors, small modular reactors, and it's not clear to me that the cost per kilowatt installed is any lower than the large reactors. So how do I bring down the capital cost, basically?
Yeah, the cost of energy is a very important point. Thank you very much for your question. I have here this another picture of how many plants, nuclear power plants, has been closed in the last years. And you can see here, for instance, the US, in total almost 20 nuclear power plants are closed in the last years. And here is the motivation is the market. As you said, yeah, the market in the US is more expensive, the nuclear energy. If they want to extend the life 40 years and 60 years, they have to invest a lot of money. But they said that they should recover in 20 or 60, 30 years. But after 40 years, if they want to operate in long-term operation, it means that they have to invest a lot of money. So they have just a balance. You have to invest a lot of money. I cannot recover because the price of electricity is very low. But here in Spain, we have a good example. For a few years ago, all the companies in Spain, they said, okay, let's go to dismantling all the nuclear power plants after 40 years. Why? Because the price, electricity price, if we see the future in 2030, the electricity price is very low because we have a lot of renewables and so on. But we can see now that the Ukraine war, the situation now is different from 20 years ago. So the cost of the electricity that they said that we have in 2030 is not true. and now we have more than 100 euros. So the cost of electricity is, in some cases, is mandatory to close the nuclear power plants. In other countries, is the policy. In other countries, is the technological probably the accidents, as Fukushima accident. Yeah, but the cost of the electricity is very, very important. Regarding the small modular reactors, yeah, you are right that the small modular reactors, you compare with different technologies. But for instance, if you go to the Westinghouse and you can see the new scale is very close to the nuclear power plant, very similar to a nuclear power plant that now are operating. There are not many changes. That just the power is the 300 electrical megawatts, so they can do that. But if you propose a very challenge, a very dramatic change in the nuclear molten salt reactors and so on, I would say the technology is not clear. I don't know, but it depends on the cost. Yeah.
Oscar, may I say something? Just a little thing.
Please.
Professor, one of the questions is the law. To build a nuclear power plant usually is a private investment, so it's very costly. If you have a legislation that really guarantees you that there is not to be any changes in legislation, you will invest. If you have a legislation that is not strong enough to guarantee you that your investment is going to be sure, you don't do it. So it's a question sometimes of regulation and law, not only of perception. I think,
yeah, for sure.
Oscar.
Yeah. Totally agree.
Excuse me.
I would like you said that one of the things is I thought it was not you have a problem, but you said it's positive is with the thermal budget, because the thermal you say we can make heat, but this is maybe one of the problems that we saw people asking how you can control the heat, because you for recirculating on the nuclear power stations, you are heating the water, and you said that this could be a positive. Yeah. How you turn a negative in a positive?
For heating?
Yes.
Well, you can produce
no,
heat.
I know, yeah, you produce heat, but this is, and this you elevate the temperature of the ocean as well, because you are, this is what we saw in Japan and so on. No, how you take advantage of the heat that you produce? This is my question.
The heat, you can produce heat, but don't without the conventional light water reactors. You can produce heat with reactors that they use gas as a helium gas and so on. So you can reach this thing.
But with helium gas, the price is up.
Yeah. Here, this one. Yeah, this one. Yeah. But they said that, okay, this is not light water reactors. There are other kind of reactors using molten salt euthetic systems and other kind of no water. So for these reactors, here, for instance, you have here new scale. This is a light water reactor, 300 degrees Celsius, but if you want to move up, you have to use another kind of refrigerators. For instance, molten salt reactors, reactors with gas, and so on. But I think I have seen the results from the Japanese systems, and they said, okay, they are able to do that.
Yes, thanks for this excellent and very informative presentation. I'm asking whether the society is fully aware of all these novelties concerning the new nuclear power plant. Because, for instance, in Italy we have a votation that we will not build a nuclear power plant forever unless we have a new votation against, which will be very difficult, and it will take 30 years, 40 years to build up a new nuclear power plant. So there are so many concepts, and I'm asking whether the society, the normal people, is aware of all this novelty, and is able to understand that the risk is reduced according to these new techniques. Thank you very much.
Yeah, thank you for your comment. I think I agree with you. So the society is very important, and to educate the society is a very important role for us.
It will take a lot of time.
Yeah.
Italy, exactly, in the parliament vote no to nuclear energy, but in Italy is the Joint Research Nuclear Center, the most important in the European Union. So it sounds a contradiction, okay? So the more important research nuclear center is in Italy, but so sometimes it's something that escapes to our, is out of our, decisions.
Yeah.
Yeah.
Well, we have coffee, so we can ask as many questions as you want to the speakers.